Heaps are trees with a superpower. They always know who's next. Today we'll cover what a heap actually is, the two flavors, Min-heap and Max-heap, why heaps are stored as arrays, Python's heapq module, where heaps show up in real software, and finally, when a heap is the right tool for the job. A min-heap is a binary tree with one strict rule. Every parent is smaller than or equal to its children. That means the smallest value in the whole heap is always sitting at the root, ready to grab in constant time. Notice we don't care about left versus right ordering, only parent versus children. The tree also has to be complete, filled level by level, left to right.
No gaps.
A max-heap flips the rule. Every parent is greater than or equal to its children. Now the largest value lives at the root. Same shape, same completeness requirement, just inverted comparison. In Python, the standard heapq module only gives you a min-heap. To get a max-heap, you push the negatives and negate again on pop, a classic interview trick. Here's the clever part. Heaps are stored as arrays, not as trees with pointers. Place the root at index 0. For any node at index I, its left child sits at 2i plus 1, its right child at 2i plus 2, and its parent at I minus 1, integer divided by 2.
No pointers. No per node allocation.
Just arithmetic on contiguous memory. Cache-friendly and fast. Python's heapq module operates on a regular list. There's no heap class. Heappush adds an item and bubbles it up until the parent rule holds. Heappop removes the smallest, moves the last element to the root, and sifts it down. Both are O of log n. Heapify rearranges an arbitrary list into a valid heap in linear time, faster than you'd expect. That's the whole API. Heaps power systems you probably use today. Priority queues for task schedulers and event loops. The next thing to run is the highest priority. Dijkstra's shortest path algorithm uses a heap to always pull the closest unvisited node. The top k problem, find the k largest values in a stream, is a heap of size k. Heap sorts in place in O of n log n. Even your operating system's timer queue uses 1. When should you reach for a heap? Use 1 whenever you need the minimum or maximum repeatedly. Use 1 for priority queues, order by priority, not arrival. Use 1 for top k problems on streams. Avoid heaps if you need sorted order across all elements. A heap is only partially sorted. And avoid them if you need fast lookup by value. Heap.find is linear time. Heaps are deceptively simple, a binary tree with one rule, stored as an array. But they're the secret sauce behind priority queues, schedulers, and shortest path algorithms. Once you spot the pattern of always pull the smallest or always pull the largest, you'll know to reach for one. Next up, sorting algorithms and how to pick the right one for the job.